15 years ago, I was in the spot where you guys are today. I was in a college lecture series, and we were talking about sea launch. An engineer had come to talk about sea launch and what he was doing. And in that college lecture, I sat in the very back of the room. So all you in the back of the room, that was me. That's where I sat. All right? And this engineer proceeded to tell us how technology was evolving and things were changing. He talked about how NASA was going to be obsoleted and that the private companies would take over the space race. And what we would start seeing is more and more missions launched from space, launched from Earth to space by private corporations. And as I thought about that and I sat in the back of the room, I thought, no way that that's going to happen. Right? There is no way a private company can compete with a government organization. That evolution has moved forward. If you think about what's happening today, there's over 40 private companies today operating missions to space. Some of these you have heard of, SpaceX. I recently returned from Cape Canaveral and had the opportunity to see the SpaceX launch platform. And it was amazing to see over 15 years the technology that was changing and what was happening and taking place. As I started out, one of the things I'm going to talk to you guys about today is big data and how that's impacting every engineer and anyone involved in the technology industry today. Big data is going to change how you do business and how you think about problems. But before we get started, I want to kind of give you a little bit of introduction on IM Flash.
Here's the thing that makes life so interesting. The theory of evolution claims only the strong shall survive. Maybe so. Maybe so. But the theory of competition says just because they're the strong doesn't mean they can't get their asses kicked. That's right. See, what every long shot come from behind underdog will tell you is this. The other guy may in fact be the favorite. The odds may be stacked against you. Fair enough. But what the odds don't know is this isn't a math test. This is a completely different kind of test. One where passion has a funny way of trumping logic. So before you step up to the starting line, before the whistle blows and the clock starts ticking, just remember out here, the results don't always add up. No matter what the stats may say, and the experts may think, and the commentators may have predicted, when the race is on, all bets are off. Don't be surprised if somebody decides to flip the script and take a pass on yelling uncle. And then suddenly, as the old saying goes, we got ourselves a game.
For the past 10 years, I've been a part of a pretty amazing team. When we entered the NAND market space, we entered in 2006, and it was a pretty tough environment. We were behind in the technology process that we needed to make advances rapidly. We did technology generations. Normally what we call is Moore's Law. Some of you may have heard of it. And what that means is the memory density doubles about every 18 months. In order to compete with the competition, we had to pull that in. And we were able to defy Moore's Law, and over a 3-year period, we introduced 3 new technologies and went from last place to first place. And what you're going to see through some of this video is the industry that we're fueling is driving information. Information sharing across the world is driving the big data revolution. Modern day manufacturing is not the same. We now live in a global economy. Automation rules modern day manufacturing. If Henry Ford could look back and see where we're at in manufacturing today, he would be blown away by what we're able to accomplish and what we're able to do. Thousands of pieces of data are grabbed, analyzed, and understood every minute in a factory. Just to kind of give you guys a couple statistics, I want to walk you through a couple things you may not know. Have you ever thought about what happens in an internet minute? All right? From 2013 to 2014, right, we have right now over 3 billion users on the internet. 3 billion. Right? In 1 minute, you have over 67,000 photos being uploaded. In 1 minute. Where's that all the information going? You have over 400,000 tweets. There's over 4 million Google searches in a minute. Over 300 hours of video being uploaded. Amazon, this is crazy. Every minute, they sell 80,000 products. Every minute. And then finally, you just think of the number of the emails that are sent. 136 million every minute. That's a mass amount of data. Experts have estimated the amount of data generated worldwide will reach 1.3 zettabytes. Who here knows what a zettabyte is? Raise your hands. All right, so a few of you. I'll introduce you a little bit more to it. To kind of give you the scale of what that means, that is the informational equivalent to everyone on Earth receiving 174 newspapers every day. Right? Huge amounts of information, all right? So you think preparing for that class or reading that lecture, not a big deal, the amount of information that's coming across the internet. Right? To put it another way, if 1 bit of information equaled a star, the amount of information we store is like a galaxy for every person in the world. That's how much information that we're storing. I swear, geeks name all these things, all right? So how big is a yottabyte? Okay, most of you have heard of a megabyte, a gigabyte. Now you're starting to hear of a terabyte, right? Most of you may have a terabyte that you store a bunch of photos on, right? So a terabyte is, you got to think of it just a solid drive, all right? Today, most companies are starting to operate in the petabyte range, and this is where IronFlash is. We have several hundred petabytes that we store on site that we're constantly analyzing, looking at, trying to figure out what the data tells us. That's equivalent, 1 petabyte is equal to about 2 data center cabinets. An exactabyte, right, much larger, that's about a 4-story data center, right? That will take up an entire city block. Many of you may have heard of the Utah data center, all right? That's the NSA that's listening to this conversation right now, all right? They store anywhere from 10 to 15 exactabytes. And then you hit really where the World Wide Web is today. That 1.3 zettabyte number, right? That's 1,000 data centers. That'll take up 30% of New York City just in that data center alone. Yottabyte comes next. That's over 250 trillion DVDs. All right? The other way to look at this one, it'll be 1 million data centers, all right? And that's basically Delaware and Rhode Island. All right? Pretty amazing, pretty staggering. All this information, all of it being stored, all of it being shared across the World Wide Web. So how are we storing this information? Currently today, 94% of information is stored digitally, right? They're not in libraries, it's online, or it's stored away in some sort of database, right? We're seeing a 3x growth rate year over year in terms of how we store and how we analyze data. This is coming in all sorts of forms. How many of you are currently using an SSD drive? All right, pretty amazing. That has changed. That's happened over the last 4 or 5 years. We've just gone from solid-state drives to SSDs. Not only are you finding them in laptops, but you're finding them in you're seeing them in massive data centers. Tablet has not been a big growth market. They're a cool toy. All right, mobile continues to store. We continue to see growth here because everyone likes to take pictures on their phones and upload them to Facebook and tell us what you're eating. Consumer storage, there's a lot of applications here, and there's other devices, right? The company that I'm involved with, this is what we do. We're fueling the data revolution. So where's all this data coming from? How are we collecting it? What type of information are we collecting? Give you one more example.
This is where the wild things are. 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 Oh my God, they can't hear me.
Can actually figure out how many times you rotated, how many G-forces you left to take off with, how many G-forces you landed with. A lot of insane stats that you never find out before we can find out now.
That was awesome!
It was crazy how much information they can get from a tiny device on your board. Technology is insane, man.
People at home are now going to know what's actually happening here at the X Games.
The fact that they can get it live on TV, it's going to make it so much more exciting, you know.
Some amazing changes and some amazing ways to collect new information. That technology was not available when I left school, right? That technology has really came about in the last 5 or 6 years. Oftentimes I go on college campuses and I get the question, is Moore's Law dead? Has it stopped yet? The answer is no, right? 2015, we're seeing a big shift in our memory applications. Traditionally, semiconductor products have been built in a 2D plane, pretty similar to a city. When you have a lot of space, what do? You build in 2D. What happens when you run out of land and real estate? You go 3-dimensional. That's really the evolution of where we're headed, right? 2015, we announced a 3D NAND product, which basically looks like the city skyscraper that we've got here. And we're now able to pack more information into the same space than we ever have. This has 3x higher capacity than we've ever experienced before. And this is going to enable everyone to have a 10 terabyte drive in a 2.5-inch form factor. All right? How would you like to have 10 terabytes on your computer? Right? You can upload every video that you have ever had. Right? It's coming, and it's going to happen based on the revolution we've got going on. Right? All right, problem with skyscrapers. Where there's an emergency and you need to get out. How do you get out? It's kind of slow. It takes a little while. You have to go down the stairs, through elevators. That's a problem. If you're playing a video game, you don't like to boot up a video game and in 2 hours come back and play that video game, right? You want to make it happen right then and there, right? In July, we introduced a new product. It's called 3D Crosspoint. And this is going to be 1,000x faster than NAND. It's going to have 1,000x the endurance, meaning you can read and write to this a lot, you can get information faster than you ever have, and we're going to unlock the power of the processor. Today, most processors only operate at about 30% capacity. The reason for that is they can't get information out of the memory system fast enough. And that's what this was specifically designed to address. All right? So how good are we? August 2012, they were able to take digital information, synthesize it onto DNA, and basically program a DNA strand. Then they were able to take that DNA strand, and those proteins, pull that information off of it, and replay it. All right? Pretty amazing. As good as we are in silicon-based memory, DNA is still 1,000,000 times denser. All worldwide storage that we have today could basically fit on a gram of DNA material. Pretty amazing, right? We still have a long way to go. We're still learning from nature. Only problem with DNA, it's 1,000,000 times slower, right? When you boot up your video game, it's going to take you 3 years before you're playing. That's a huge problem, right? But is Moore's Law dead? No, right? There's a lot of science challenges that we still out there. There's a lot of information. All right, so we're now storing all this information. We have a bunch of new products that are coming on the market that's going to allow us to store it. So what? What is that going to do? What does that mean for us? Big data is changing how we do science. Let's talk about your basic doctor visit. What do? You go into the office. The doctor comes up with a question or hypothesis. What's wrong with you? Ask you a bunch of questions. They'll run a test, maybe take some blood work. They'll talk with you a little bit, and then what do you wait for? 2 or 3 weeks for that information to come back, and then the doctor forms a hypothesis and gives you information. Let's think of the differences with big data. How is it going to change this model? Right there in the center, big data is taken over. You're now going to, instead of wait for that doctor to do tests, they'll be able to grab information. You'll be able to get it from health apps, medical records, lab tests. Most of you may have a wearable that you're wearing today. Information off of that will tell you a lot about who you are and your health statistics. You'll have the genetic makeup in your genetic code, and then coupled with the population statistics, you'll have a pretty good understanding of your health and maybe even how long you're going to live. All the information will change how quickly you get information and how they make diagnosis. So is this happening today? This is my tracking statistics. All right, pulled it off my watch. There's a couple things that I learned from it. This is where I bought the watch and realized I wasn't exercising enough. All right, quickly told me I need to get it up. Here's my New Year's Day resolution. That didn't work very well, did it? Right? Up here is my heart rate. I know both the min and the max heart rate per day. I'm getting it every minute. Here's where I took a new job and quit exercising. All right? What I found kind of fascinating, I didn't know on average I'm climbing 10 flights of stairs a day. And then I have this huge anomaly here. This is a business trip I took to Asia, and the facility that I was in, we were up and down the stairs all day long. Right? All sorts of information. I've got this on my watch today. Right? This will continue to evolve and continue to grow forward. So what does this mean for engineers or anyone in the technology industry? Apparently, we're not going to be needed for much longer. All right? Stephen Hawking also said this year. Computers will overtake the human race in the next 100 years. All right? So you just got an engineering degree, you're not going to use it. All right? I'm going to tell you today, I don't know what the next 100 years is going to bring, but I can tell you right now, computers are not taking over. Currently today, we are generating information faster as a human race than we can store it. We can only store about 30% of the information we generate, and that's if we're lucky. Right? This industry is fueling and continuing to go forward. The way that I think of computers is they're idiot savants. They do some things really well. They can beat me at chess, but there's a lot of things they can't do. You got to use computers for what they're good at. So this goes into what does it look like to be a modern-day engineer or anyone working in the science fields. I'm going to walk you kind of through some 3 key points. The first one is building data analytic capability will be the key to success in the 21st century for every engineer. If you do not have data analytic capability, you will not be successful. The amount of information coming at you and where it's being stored, you're going to have to know how to get it. And there's some key skills you're going to have to do. You're going to need to have some programming skills. You're going to have some script languages that you understand. You're going to have to understand which script language is the best language to use for your particular application. Not all of them are created equal, and you're going to use different ones at different times based on the data set and based on the information that you need to get. You're going to need to understand databases. You're going to need to understand statistical computing packages. You're going to need to have some domain knowledge and some skill sets. You're going to need to be passionate about the data. You're going to have this hacker mindset, and you're going to need to be curious. Where can I get information from? What is that information telling me? You're going to need to have math and statistics knowledge, right? Not just good enough to be a good mathematician, but you need to understand how that math works together, how statistically use it, good design of experiment, and also good modeling capability. Finally, you're going to need to be able to communicate and visualize that information, right? Data's boring. Data won't get your project to be pushed forward. You're going to have to take that information, manipulate it, put it in some sort of graph, some sort of chart, some way to visualize that information so then the managers and the other individuals that you're trying to influence understand it. So if you're taking art, that's a good thing, right? It will help you as you move forward as an engineer. Engineers of the future will also know the data scientific method, and this is slightly different than the scientific method in the past. Like any sort of scientific method, you're going to ask a question. You're going to do some research to make sure that you're asking the right question or trying to solve the right problem. You're going to form your hypothesis around that. But what's different now, instead of running test after test, you're going to go find a data set that's going to tell you the answer. You're going to test that with data, you're going to analyze it, and then you're going to either accept or reject the hypothesis that you came up with, and then you're going to find, wait a minute, I didn't have the right data set, and then you're going to repeat this process over and over and over until you finally come to a conclusion. All right? This is being done today, so I'll give you a couple examples of how it's taken place. Most companies are worrying about, hey, we're losing people. How do we keep them? I need to give them more pay. If I give them more pay, they're going to stay. Right? So do you pay your prize employees to keep them from jumping? Do you pay for gripes, complaints? Well, today you can go out and you can gather all sorts of information statistically from various websites about why people are leaving companies. And you know what big data says? Increasing pay to the midpoint is every bit as effective as paying to 10% above the midpoint. Really basically tells you it's not all about pay. There's other reasons why people are leaving you. Pretty simple, straightforward, but the information is out there. Here's a little better one that I came across, right? Heavy loads. So the London Underground has been suffering from congestion problems, and they're wondering, do I need to install additional escalators, right? During peak times, people are waiting in line anywhere from 45 minutes to an hour to get up. Well, you can take those peak time information, they load it into an algorithm, and guess what they found out? They don't need more escalators. They just need people to stand side by side instead of stop using them single file. That solves all the problems. All right? Good luck getting everyone to side by side. Doesn't happen. Finally, UPS on the gas savings. What is the best routing method to save money on fuel? All right? So they took something from BYU and they chose the right. So they used their GPS data, they tracked their systems, and they tracked their trucks, and they found out that routes with only right-hand turns are more efficient even if they're longer. Right? Saves money, saves gas. Right? They also saw their accident rate significantly go down, all from big data.
With nearly 100,000 trucks and hundreds of aircraft, UPS averages 15.8 million packages delivered daily worldwide. While an individual person may not save much by only making right turns, since UPS implemented a right turn policy in 2004, they have significantly increased profits while reducing emissions and accidents. UPS estimates the right turn heavy policy combined with its routing software shortens routes by 20.4 million miles and saves 10 million gallons of gas while delivering an additional 350,000 packages and reducing CO2 emissions by about 20,000 metric tons each year. UPS engineers noticed how waiting to turn left caused trucks to fall behind on their schedules, consume more gas, and increase the probability of accidents. Their software maps routes with only right-hand turns, unless it's quicker or easier to proceed with a left-hand turn. A driver estimates they do about 90% right-hand turns. The television show Mythbusters tested the policy with one route using 8 left and 4 right turns, and another route using 1 left and 23 right turns. The UPS-like route was just over 1 mile and 9 minutes longer, but it reduced gas consumption from 6.8 to 4 pounds. UPS's software probably would have added 1 or 2 more left-hand turns to be more efficient on time, while still saving gas.
All right, real-world applications for big data, right? It has changed how we look at things and how we solve problems. My point number 2, engineers of the future will focus relentlessly on getting good data and keeping that data clean, all right? Not all data is created equal. Right? There's a lot of information out there that's just not right. But most importantly, data has to be acquired, and once you acquire it, then you need to manipulate it, right? Engineers should understand the difference between causation and correlation. And I got some couple examples to kind of explain that to you, right? But there is a difference. You're going to focus relentlessly on keeping that data clean, right? Healthy organizations will put data to use. They'll make it easy for everyone to have access to that data. Everyone will use it, and it'll be expected to use it. There'll also be lots of teamwork as you move forward. Lots of brainstorming, lots of dumb ideas, lots of tests that turn out wrong, right? But more importantly, you're going to have constructive confrontation, right? But you're going to have to support your arguments with data. That's one of the key things I was taught. The first day on the job, I was told, trust God only, everyone else brings data, right? You bring data to support your argument. And that's one of the key things for every engineer. Find it, understand it, keep it clean. Moves into kind of the engineering skill set, and there's a couple places we've got here. There's 3 core skills of every engineer. You need to be a substantive expert. You're doing that now. You're in school. You're learning some sort of background or information about what you do, whether that's engineering or information technology. You know, you're getting into the details and becoming an expert in the field. But it just doesn't stop there. Here's where the hacking skills come in. You've got to figure out how to get good data and good information. Then you need to use your math and your statistical knowledge to kind of put all that together. There's a couple danger zones. So between the expertise and the math and the science skills, this is traditional research. This has done great for the past 400 or 500 years, right? Today it's not fast enough. If you continue to operate just between this and do traditional research the same way, you will be surpassed by the global economy. You are absolutely entering a space where you're competing globally with people across the globe, from China to India to Asia. And they know the power of big data, and they're using it. And they will solve problems faster than you will if you don't get on the revolution with big data. You have this space up here where you got hacking skills and you're an expert. All right? This is a risky space. If you're not using sound statistical modeling, you're going to draw incorrect conclusions, and it's going to lead you down the wrong path, and you're going to be solving the wrong problems. Finally, if you have hacking skills with machine and statistical knowledge, you're going to constantly find correlations and never come to causation because you can never connect the dots. So how does this look? I'll give you a prime example. All right? Keeping your data clean and using your statistical skills. So again, hacking skills with the substantive scientific expertise without rigorous statistical methods will lead to incorrect conclusions. This chart may not mean much to any of you guys. That picture in the background is what we call as a probe card. All right? So the industry that I work in, we produce NAND memory products. All right? And it comes in a wafer that's about 12 inches. Right? And there's about 300 what we call die on there. Right? Every one of those die works its way through the manufacturing line, goes to what we call probe, and this card is then used to touch down on it and test it to see if it's working electrically. All right? Okay, no big deal. You're testing it, so what's this data? All right? There's over 64 billion bits on every one of those die. Billion. Okay? Explain to me how you're going to chart 64 billion bits on a graph. You don't. All right? And we can't. So what do? We truncate the information. We use scripts and algorithms, and we put that information down in a more digestible format that we can understand, which represents a graph of information. This is an electrical parameter that we're exploring, we're wanting to understand. Well, we came out with this electrical program after we tested it, truncated the information down, and got the information out of here. And we started then running correlations and trying to figure out what's wrong with our product that we're producing. Couldn't find the solution, multiple engineers working on it. We finally thought we had the path, continued to work down the path just to find dead ends and never really find the root cause of our problem that we were suffering from. One smart engineer recognized and said, wait a minute, this data set looks like it has multiple distributions. Statistically, that can't happen. This doesn't make sense. He quickly went in, looked through the code, and found a bug in the code. It was randomly throwing information. So we were getting ones and zeros, zeros and ones. There was no correlation. He cleaned up the probe code, and out popped a better Gaussian distribution. Right? Within the next 2 days, we were able to find the problem, solve the issue, and move on to the next problem we needed to solve. Right? The importance of understanding statistics. You need to make sure you understand what you're looking at and what the data is telling you. Causation does not equal correlation. This one's kind of interesting, right? We have millions of pieces of data being stored. And just to give you an example, today's modern-day manufacturing plant, ours alone, we have 800 machines, right? Quite a few. We have over 400 processing steps. Of those steps, we're monitoring about 150 parameters, right? All this information is being loaded, always being captured. So what does that mean? 48 million data signals are being captured almost every second, right? These are staggering numbers. You're like, wow, that's an amount of data. Well, how do we use this? This information is then taken, and we take this tool signal database. We take all the information, and what do? We put it right in that database, and we store it. Right now, we can only store about 6 months of this information before we have to purge it off because we run out of space, right? So now all that information is out there stored. So how do I use it? Talked about before. We have wafers, all right? This is what a wafer looks like. All those individual squares are the die. We'll go out and we'll electrically test it, and we'll say, hey, wait a minute, I've got some good ones, and I've got some bad ones. And a good data scientist or good data engineer will say, aha, I've got a database that's got a bunch of parameters in there that tell me what went right or what went wrong with the process. So they'll take that information, they'll use a tool database, do some scripting, and out will pop over 1,000 correlations. All right? No closer to solving the problem. And this is normally what we see, about 1,000 correlations coming out, right? There's only one causation through all of this. The way to look at this is, say you're investing shark attacks on the beach, right? So you go, you're investing the shark attacks, you gather a bunch of data, gather a bunch of information, you run an analysis, and out pops, ice cream sales are correlated with shark attacks. Fantastic. I'm going to quit selling ice cream, and that's going to solve my problem, right? That's correlation, right? The engineer has to then connect the dots. Wait a minute, why would I have higher ice cream sales on the beach? Maybe it's a hotter day. If it's a hotter day, maybe more people in the water. Now you've made the correlation and you found the causation. It's hotter, so more people in the water, which results in more shark attacks. These are things that you have to connect. This is the thing that a machine can't do, right? This is what we need engineers for. Finally, technology is changing fast, so engineers have to stay up to date and constantly learn. All right? Your engineering education is your foundation. However, you'll need to be learning new things to keep up. A lot of talk in the news lately from political candidates around free education. I'm going to let you in on a little secret. Your future education is already free, right? As you move out into the workspace, you're going to find that there's information on the internet, through peers, through journals, through conferences. All that information is out there and available to you, and it's going to teach you and you're going to learn. But you have to be curious about the information. You're going to have to go find it. Your homework doesn't end here. Everyone thinks, done with school, no more homework. It's not the case, and that's not how it works. You will have to continue doing homework. I want to kind of leave with my final story on this. 2011, I decided to go back and get my MBA. I'd worked my way up through the engineering ranks of the company I was working for. Finally came to a place where, hey, I've been a manager for a long period of time. I want to go learn some additional skills. So I decided to go back to school, and I spent the next 2 years learning about accounting, finance, marketing, HR, all the things that engineers are not supposed to be good at. At the very end of all of this learning, we had a big grand final project, all right? And so they divided the class up into teams, right? 4 of those teams were assigned to go explore and investigate a disinfectant, all right? When you think disinfectant, that's exactly what it is. It's a biocide that kills germs, right? Each team was to go out, and we were hired by a group of investors. These group of investors had come and found a new product. An inventor made a lot of claims about this product, and this new product was supposed to be the next greatest thing. And our responsibility was to understand, what is the market for this product? How are we going to sell it? Right? What's the potential? These investors were going to have to invest a significant amount of money to get the FDA clearance, which is not cheap. That can range from anywhere from $1 million to $6 million. And our responsibility after 2 years of going through school, learning all these skill sets, was to bring all of that together, right? And then we would then go back and present to these investors and say, yes, move forward with buying this product, move forward with the investment, and enter this market spot. So each team ran off thinking, great, I've got this fantastic idea. All right? So here's kind of some of the assumption we were given. You know, imagine a disinfectant that has all this capability, safe and effective, low toxicity. It's great for the environment. It's got this great shelf life. It's low cost. Everyone likes cheap. Right? Nothing like it in the market, doesn't break down, and it's non-corrosive. Pretty amazing claims, right? So what type of business is this? Just look at the potential. These are just a few companies. This is a multi-billion-dollar business, right? So a disinfectant that doesn't harm humans and kills just germs, this has got to be the best thing ever, right? I should be able to go sell it. Okay. 3 of the teams that we were working with, so there's 4 of us, our end grade dependent upon it, 3 of them took all these claims and said, fantastic, guess what I'm going to go do? I'm going to go find the market that's going to sell it. Right? So as we walk into the last presentation, it's pretty amazing. We got to go last as a team. Right? One thing that I recognize is, hey, I know nothing about the biocide industry. I know nothing about the claims being made, and I need more expertise. So as a team, what we decided to do is we decided to go out. We found a professor here on campus. This is what they knew everything about. We showed him the different claims that have been made and all the product features, and he was like, yeah, those are pretty good. He reviewed the data with us, walked us down through it. Yeah, that's pretty good. That's no different than what's out there on the market. Here's something else. And over the next hour, he proceeded to tell us and educate us on what was taking place. Within the next little bit, what we discovered, companies O and M had similar products on the market, but one thing that we discovered was they already had FDA clearance. They had already jumped through the hurdles. They then just told us about a new product that had just entered the market. What did we find out? Same exact product claims, already had FDA approval, was already 2 or 3 years ahead of this product, and was a completely different scenario. Right? We were working for the investors, not the inventor. Our responsibility was to go out and understand the market space and understand the landscape associated with it. Our team was last. Team number 1 got up, talked about the potential, talked about how amazing this was going to go, told the investors, you guys need to purchase and buy this product. Team number 2 repeated that exercise. Team number 3, the exact same exercise. Finally, our team got up there, we presented our information, and we shared the facts that we found, and our recommendation was, don't invest in this product. Right? All from doing homework, asking questions, and going out and getting information that we didn't have at the time. Huge learning experience for me as we went through that. Right? Not making a mistake. These were smart individuals, 2 years of schooling, all to fail. Right? At the end of our presentation, the investors came up and thanked me and appreciated that we'd taken the time to really explore and look at it. The inventor came up at the end and said, you must be a chemist. And I said, no, I'm a realist. And that's one of the things you have to look at. You have to have questions. You have to look at the data, and you have to do your homework. Too many engineers today don't take the time to go do their homework and understand the problem in an effective way. So in summary, building data analytics capability will be the key to the success of the 21st century for every engineer or person working in the technology field. You have to have this capability. You need to leverage humans for what they're good at and machines for what they do best. There are things that machines do better than us. Use them. Engineers of the future will focus relentlessly on data and getting that data and keeping it clean. If you don't know how to get it, you're going to figure out how to get it. And finally, technology is changing fast, so engineers must stay up to date and constantly learn. Your engineering education is your foundation, and BYU is setting you up for success. However, it's only the first step, and the journey's still ahead of you. Thank you for your time.